So let's formalize the result of our three examples from Wednesday. If we have our characteristic equation for our recurrence, and we solve that quadratic, and we get two roots, R1 and R2, then the recurrence has a solution, alpha 1, R1 to the n, plus alpha 2, R2 to the n. Alpha 1 and alpha 2 are constants. I think I called them capital A and capital B on Wednesday. So as long as I can solve the quadratic equation, I'm good to go. Seems simple, yes? There's just one problem. That sentence is not always true. Two questions. First, what is the characteristic polynomial for this recurrence? Second, what are the roots of that equation? Means I need to turn this into a quadratic, right? Advantage, in my theorem, it shows how the quadratic is related to the recurrence. So I don't have to go through the procedure we went through on Wednesday of replacing the an with an r to the n and then dividing and all that. I know this number, C1, is here. This number, C2, is here. I'm going to move those to the other side. So the corresponding polynomial looks like this. I move the an minus 1 to the other. That's why that's negative. Move the an minus 2 to the other. That's why this one is positive. So they switched signs when they went from the right side to the left side. Wonderful, marvelous piece cake. Roots. What are the roots of this polynomial? Quadratic. Factor it, quadratic formula, complete the square. I don't care which way you want to solve it. Plug it into a graphing calculator and graph it. Ask ChatGPT and let's see if it hallucinates or not. What are my roots? And just 2. Because this is r minus 2 squared. It's only got one root. It's a root of multiplicity too, if I go back to my algebra class and think about what that means. It touches the x-axis, it doesn't cut through it. Vertex of this parabola is right on the x. Oh. Now I can't use this. This solution only applies in the case where I have 2 distinct roots. Now, why? When I came up with the 2 roots, I said, hey, look, this works as a solution. This works as a solution. And I can show each root, r to the n, worked perfectly as a separate solution. And then I could make combinations of them. But if I've got the same root twice, when I combine it, it's really the same thing, isn't it? I need 2 separate, independent solutions. And that independence idea is actually linear independence from linear algebra, or independence of functions from functional analysis, which is really an extension of linear algebra there. I need something that, quote, points in a different direction as a function. So I want to use 2 to the n. But I can't use it twice. So maybe I'd have something that looked like this. But that's only one of the 2 pieces up here. And if I've got a quadratic, I should have 2 pieces to my solution. So in order to make the other one independent enough to make it go in a different way, I'm going to use the following trick. And I'm going to add a factor of n. This extra factor, this extra multiple of n, allows this function to be different enough to be considered independent of 2 to the n. I promise there is a formal definition of this independence. If you're interested in looking it up, it's called a Wronski, after Joseph Wronski, a Polish mathematician of the 1800s. I'll talk more about that in a differential equations class. We'll talk more about it in linear algebra. If you have or haven't taken that, it's a determinant. But I promise this works. You don't have to believe me, but explaining it's going to take longer than the rest of this class period. So let's see if this works. If this works, I should be able to solve for alpha 1 and alpha 2 using my conditions. And then I should be able to check that that function makes the same sequence as my recurrence relation makes. So if this is my an, the fact that a0 is 6 tells me what? If it's A0, I can plug in 0 for n. Wait a minute. What's 2 to the 0? 1. So this is a 1. But what happens over here? That's 0. So what this tells me is that that's just alpha 1. I just found the value of alpha 1 right away. I like that. A1 equals 8. Equals alpha 1 times 2 to the 1 plus alpha 2 times 1 times 2 to the 1. Oh, wait a minute. That's 2 alpha 1 plus 2 alpha 2. Well, what's alpha 1? 6. I don't need a set of parentheses for that part. Started to write them, don't need them. You just told me alpha 1 is 6. I can solve for alpha 2 now. 2 times 6 is 12. I subtract it over, I get negative 4 is 2 alpha 2. Alpha 2 is negative 2. So that means my AN should look like 6 times 2 to the n minus 2 times n times 2 to the n. Or if you'd rather factor the 2 to the n out, I can write it like that. When I put in 0, I get 1 times 6 minus 0. A0 is 6. When I put in 1, I get 2 times 6 minus 2. That's 2 to the 1 times 4. That's 8. I can go A2, A3, A4. I can check and see if this matches what this produces. Or I could check it the hard way. What do you mean check it the hard way? That's my recurrence relation, yes? This is our expression for AN. So what is AN minus 1? Using this formula. Just replace your n with an n minus 1. What's AN minus 2? Same thing with minus 2. Now, take these two things and put them in this expression. 4 times AN minus 1 minus 4 times AN minus 2. That's 4 times this garbage. Minus 4 times this garbage. And now I'm going to do a crap ton of simplifying. And hopefully, when I do all that simplifying, I'm going to end up with this. Because that would be AN, wouldn't it? Let's see if it works. Wait, 4 is the power of 2, isn't it? What happens if I combine these? I just rewrote my 4 as 2 squared. What happens here? Multiplying with the same base? Powers add, so I get 2 to the n. Which is good, because that's what I want, right? Here I'm going to get an extra, right? This will be 2 to the n plus 1, right? Rather than do that, I'm only going to move one of the 2's. So now I have 2 to the first times 2 to the nth instead of 2 to the n plus 1. Why am I doing something stupid like that? Because now I can factor the 2 to the n out, because up here that 2 to the n is factored out. So let's factor it out. And now look at everything else we've got. I've got 2 times 6 minus the quantity 2n minus 1 minus 6 minus 2 quantity n minus 2. Ryan, you're looking at me like I just slapped in the face with a fish.
I'm just confused where in the second line, yeah, how it goes from 2 squared times 2 and minus 2, and then right below it's just minus 2n.
Ah, because what happens when I multiply these? I add the powers, 2 plus n minus 2. And then the same thing happened here, because 2 plus n minus 1 is n plus 1, but I left 1 separate from the other n. Okay, now I'm going to try and deal with all this crap. I've got 2 6's, that's a 12, minus 4 times the quantity n minus 1, minus a 6, minus a minus becomes plus, 2 times the quantity n minus 2. Wait, 12 minus 6. How good? I'm already happy. 6 minus 4n plus 4, right? And then here I get plus 2n minus 4. What happens to 4's? And I'm left with minus 4n plus 2n. And that's exactly what I wanted to end up with, isn't it? Phew! It worked! Which means I can now write a version of Theorem 1 that applies to repeated roots. I want to write it basically the same way I wrote it before. Suppose r squared minus c1r minus c2 equals 0 has one real root. Then the recurrence relation an equals c1 a n minus 1 plus c2 a n minus 2 has a solution of the form an is alpha 1 r to the n. Sorry, I'm going to write that r0. r0 to the n plus alpha 2 n r0 to the n, where r0 is the root and alpha 1 comma alpha 2 are real numbers. So if I have two roots, I get an alpha 1 and an alpha 2, and I get each root. If I only have one root, I only get one shot. And I get this extra n thrown in to make it different enough. Questions? I would point out to you that there is still another option. What's the still another option for my roots? I need to be a little more specific there, because every quadratic equation has roots. But if I don't have two real roots, I don't have one real root, then I have complex number roots. It is possible to actually do this same idea with complex numbers. That is beyond the scope of this course. Now, the reason I bring this up is because two of the most commonly used equations in physics are based off of these recurrence ideas with complex numbers involved. And you've seen them already. Simple harmonic motion, a pendulum, a spring on a mass. If you take physics, you've done those experiments in lab. And they work for exactly this reason. They just end up with complex numbers. Especially when you take friction and resistance, like a shock absorber, which takes a bounce and doesn't just keep bouncing forever, although the roads outside might convince you otherwise. Your shock absorber is designed to slow that vibration. Our pendulum will eventually slow down and come to a stop. So that's in here, but only in the complex case. More on that in differential equations. So how can I generalize this idea? If I don't want to do the other cases for the roots, I should do other cases for the degree. This is a degree 3 recurrence. Because I've got an minus 2 and an minus 3 in here. I don't have any an minus 1s. That just means the coefficient for an minus 1 is 0. Since it's degree 3, I need 3 starting conditions, because this expression is only useful when n is bigger than or equal to 3, which is why I need a0, a1, and a2. Here is my absolute favorite thing about this. Everything we've done Wednesday and today so far still works. And it works exactly the same way. If I can find the solutions to the characteristic polynomial, those will be my roots, those will be part of my general solution, and then I'll just have to solve for the constant. So, I'm going to ask you the same question I asked earlier. What's the characteristic polynomial for this recurrence? What are the roots of that polynomial? When I did a degree 2 relation, I ended up with a quadratic, right? If I do a degree 3 relation, I should end up with an r cubed. So I'm going to get an r cubed here. And then for every step down in the subscript, I step down in the power. So on the left, I have this r cubed. On the right, I'm going to have no r squared, because I don't have any n minus 1s. I'm going to have 7r and 6 times r to the 0. In other words, my polynomial becomes r cubed minus 7r minus 6 equals 0. And now we get to the ugly question. What are the roots of that? I'm going to cheat, and you should too. Do you know the cubic formula? Cardano's formula, Tartaglia's formula for solving a cubic equation? Me neither. Graph this sucker. I can't see squat over there. We'll put it over here. X to the third minus 7x minus 6. Graph. There are my roots where it crosses the x-axis. And there are 3 of them. There are 3 distinct roots here. Perfect. R equals -2, R equals -1, R equals 3. Because that's where I go through the x-axis. Now you could do that algebraically, because if you go back up here and you look, you'll notice that when you put in -1, -1 cubed is -1. -1 times -7 is +7. So I have -1 plus 7 minus 6. So I might have been able to get one of the roots by inspection and then done long division to divide that out, and then I'll get a quadratic and I'll be able to factor that. Sure. That would have taken me about 6 minutes. This took less than 1. I like this idea. And yes, these problems will be rigged so I can do this. Now, if this is my set of roots, what should my solution look like? What's my AN expression? I want to parallel what I did with the quadratic case. By the way, you don't have to use alphas. You can use whatever letters you want there. I just don't want to use R, because I already spoke for that one. But my three roots are -1, -2, and 3. So I'm going to write something times -1 to the n, and something times -2 to the n, and something times 3 to the n. Just like I did with 2 of them. Just now I have 3 of them. Oh no. What error shall I do? I have 3 initial conditions, don't I? That means I can write 3 equations to solve for A, B, and C. 3 equations and 3 variables. A0 is 9. What happens when I put 0 in for all of those n's? Say again. Exactly. Because -1 to the 0 is a 1, -2 to the 0 is a 1, 3 to the 0 is a 1. So I get A times 1 plus B times 1 plus C times 1. I'm going to reverse the two sides. I'm going to write A plus B plus C equals 9. What happens when I put in 1?
A minus B plus C.
Oh, careful. Those are -2 and 3 raised to the first power. So while you're right here, I get -1 to the 1. Here I get -2 to the 1. So it'll be minus 2b. And here it's 3 to the first, so it's plus 3c. Second equation in 3 variables. What happens with A2? So now to find A, B, and C, you have to solve 3 equations in 3 variables. Remember how to do this? Maybe. You do elimination by addition to get rid of the same letter in 2 of them. And then you have 2 equations in 2 variables, and then you reduce that. This is long. It's not difficult, but it's long. So if I number these equations 0, 1, and 2, because that's what they were, I can say I'm going to take equation 0 and equation 1. I'm going to add those together. When I add those together, the A's cancel. And I get -b plus 4c is 19. If I take equation 1 and equation 2 and I add, the a's will cancel. And I'll get 2b plus 12c is equal to 42. And now I have two equations in two variables. I can do that however you want. Multiply the top equation by 2. Add those and I get 20c equals 80. C must be 4. Now I can go back here and I can figure out the value of b. Minus b plus 4 times 4 is equal to 19. That's 16. If I move it to the other side, I get minus b equals 3. So b must be equal to negative 3. Now I can go back up to one of these equations and I can solve for a. A plus b plus c is equal to 9. So a minus 3 plus 4 is equal to 9. And that means that a is 8. And now I know an. 8 times minus 1 to the n minus 3 times minus 2 to the n plus 4 times 3 to the n. Phew! Worked, master, it's worked. As long as I can do two things, find the roots of my equation and solve the simultaneous equations for the coefficients, I'm good to go. This even works if my roots are repeated here. So let's suppose, I'm not going to do one, but let's suppose that I ended up with 5 roots. And the 5 roots are these numbers, which I literally just pulled out of my ass. Actually, you know what? Let's make both of these 5 on the end here. Oh boy. Okay, wait a second. This means I'm going to have 5 coefficients and 5 starting conditions. I'm going to do this next part on a computer, but I need to set up the thing so I can come up with the equations. So what's my AN look like? Well, AN should have a 2 to the n in it with some number in front. And then it should have, what did we do when we had a repeat? We put on an n. I've got another repeat. I'm going to put on another n. And then I'll have a 5 to the n and an n 5 to the n because each of that one repeated, didn't it? Every time I get a repetition, I get another n because that makes it independent, different enough. Do I actually want to do a problem that's going to end up like this? No. But I don't control the problems you're going to run into in the real world, only the ones from my exams. By the way, I did this solving of A, B, and C by hand. Do you know how to solve a set of simultaneous equations on your calculator? Let's go back up here. There, I'll turn it for, oh, that's too bright. There. I want to type in these equations. But in order to put them in here, I need to put them in a standard form. And that's why I've written them lined up like this. In order for me to solve these equations in my technology, I need a matrix, which is part of linear algebra. So you may or may not have seen this before. What I'm going to do is I'm going to take these equations and I'm going to extract from them just the coefficients, just the number part. That's why all the A's are lined up, all the B's are lined up, all the C's are lined up, and all the numbers on the other side of the equal sign, they're all lined up. So I'm going to turn this into an array. And that array looks like this. 1A, 1B, 1C is equal to 9. Minus 1A, minus 2B, plus 3C is equal to 10. 1A plus 4B plus 9C is equal to 32. Those are the same things as these equations right here, just written in a slightly different fashion. Yes? So now I need to put this in here. Please notice what is written above the X inverse button on your calculator. What's it say above the X inverse button on your calculator? Hit the second, and then that. This is where I put matrices. You can see the little square brackets like we wrote for our array of numbers. I'm going to put together an array. I'm going to use this first one. You can use whichever one you want, and I'm going to edit it. Edit, matrix A. Right now, our matrix is 1 row and 7 columns. If you don't have numbers up there, you might not see anything. You might only see a single square. I need to put the number of rows and the number of columns. 3 rows, 4 columns. Now you'll notice on the right-hand side of our array in the calculator, there are these little ellipses because there's more columns than it shows on the screen at one time. Some of the smaller, more dense displays on the newer model might actually show you all 4. This is an older calculator. It is easy to remember, in my opinion, that you want to put rows first and columns second. It depends on whether you are a religious person or a soda person. RC Cola, rows, columns, or Seton Jose Roman Catholic School, RC. Take your pick. Lots of different mnemonics here. Rows, columns. Now I simply type in these numbers going across. 1, enter. 1, enter. 1, enter. See how the matrix ends in column 4? 9, enter. I get to the second row. -1, -2, 3, 10. 1, 4, 9, 32. When I hit that last enter, it's stuck. It just said, okay, I don't have anywhere else to go. So I have to hit second and quit. Takes me back out to a blank screen. If I hit the matrix button again, notice my first one is now 3 by 4. If I hit enter, it'll show it to me. Hit enter twice. Does that match what we have? I always do this. I always double check, make sure I got the same thing. Okay, now I want to do something to this. Second matrix, one more time. The middle column here says math. The matrix will do stuff. The matrix button will do stuff, all sorts of stuff. In linear algebra, you will learn this method by hand so that you know what the hell the calculator is doing. The process is called Gaussian elimination, after Carl Friedrich Gauss. It is sometimes called Gauss-Jordan. Pretty sure it's Camille Jordan, because he figured out more pieces to this. What I am looking for is something called reduced row echelon form. You'll never remember that. RREF, reduced row echelon form. See the little arrow? Work your way down. Hey, there it is. Reduced row echelon form. I want to do that to our matrix. I want to do it to matrix A. So I hit enter, and then I say second matrix. I want to do it to matrix A. And then it does it. A is equal to 8. B is equal to -3. C is equal to 4. Nothing quite like having the text save me a ton of work now, isn't it? So when I get to larger and larger systems of recurrences, larger and larger systems of equations, this is absolutely faster. 3 by 3 computationally is by hand just as easy to do this way as it is to do the elimination way. But if I don't have to do it by hand, I'm not going. Anything larger than 3 by 3, this is a more efficient algorithm. Technically, I think this is still big O of n squared. But when you get to larger and larger matrices, larger and larger systems of equations, the by hand method is a recursive method. And so it's technically n factorial steps. This is only n squared steps. It's a faster method. But since 3 squared is 9 and 3 factorial is 6, it's actually easier to do the by hand version with the elimination for a 3 by 3. Questions? It is also possible to use these same sorts of methods to solve recurrence relations like our Tower of Hanoi problem, which were not homogeneous. But in order to solve a non-homogeneous one, you first have to solve the corresponding homogeneous one. So I'm not going to do non-homogeneous cases here. I will again delay that until our differential equations course. I would like to talk about relations more in general, because this is a particular kind of a relation, or recurrence relation. And the idea of a relation is a much broader topic. So next week, I'm going to address relations in general and look at some of the particular ideas that we've already seen back in our logic chapter and our set chapter. So there's a lot of recall for this next chapter. And then some really neat happens. I will see you all on Monday. I hope you all have a wonderful weekend. You are reminded that chapter 8, section 1 is due on Monday.